This is a joint work with my former student, Sengliang Zhang. And today I will speak on the topics and the numerical solution of PDE. And what is PDE? We know the solution of the PDE perhaps is a curve or a surface, such things. And such PDE is time dependent. This means the curve or space will be moving. And how to describe a surface? A very completed surface. You cannot, perhaps not use one function, one simple function, or polynomial to describe it. And for our applied mathematics, we think that we cannot describe every element of the world. If you can take the wave equation, you cannot describe every element of the world. However, we can take a lot of leaf to put on the wave, and then you can describe the leaf, and then you know the approximation of the surface, how the surface moved. You can, for applied mathematics, we always handle the problem for discrete, always handle the problem for finite data. You cannot describe infinite many data. We always doing the finite data. And for such PDEs, this is called Hamiltonian system. And the typical Hamiltonian system is the wave equation, And a lot of such equation comes from the physical topics and geometry and so on. And the Professor Zhou said too, there are a lot of PDEs come from physics. They keep some properties such as conservation of energy conservation. For our applied maths, it's very difficult. We have only finite data, and we cannot describe the energy of the whole surface. The whole surface, we have only finite data, and we can only approximate the energy. And then you should develop a numerical system, numerical solution to solve such equations. And then will come a problem that if the energy changes, if the energy too large, and then we should ask them to come back. Should ask them to come back. And for my students, I will always ask such a problem. If you tomorrow we will to a mountain, mountain, and if you are on a mountain and you want to along the mountain to draw the contours and keep the height from the sea, what can you do? What can you do? If you take the direction of the tangent direction, then you will always go down. You always go down. It is not very suitable for us. We don't like it. We don't like it. We don't like for our life. We don't like our Earth say goodbye to the solar system, and we want our Earth always run around the sun and keep in the solar system, and then our human can live. It's a problem. Okay. In the numerical solutions of PDE, there are very famous topics. It's called the symplectic algorithms. And you can take it as a discrete conservation law. A discrete conservation law. And today we will treat such problems. And at first, yeah, I'm always working on the radial basis approximation. And at first, I will introduce the radial basis approximation. And we have a function, and the function is always approximated in such a way. And it's phi is a radial function. The function is univariate function and applied on the distance of the multivariate 2 points, between 2 points. And you can take it as a generator of such space. And then if you take the interpolation and at some discrete points, you ask this point should be interpolated, then we get an linear system of equation, and you can solve this linear system of equation. And we get this, it is my early work. You can get the approximation can be estimated as this one. And it is not only for the function itself, but for the derivatives, for the partial derivatives, higher order partial derivatives. It's a very good approximation. Okay, now we come to the equation. It's a Hamiltonian system. It's the signal derivatives in T about for the function U is equal to this one. The P is a polynomial, and this is the Guardian. And for example, you can take the Laplacian, the Guardian, two Guardian, and take the inner product of the two Guardian is the Laplacian. And here, the P Guardian is a self-adjoint negative definite operator. And usually, P is a divariate polynomial, and nabla is a Guardian operator. And such equations.
So
and
what is the degree of P? More than 2 can be 1?
More than, perhaps,
Can be 1 or
yeah, it can.
On this side is better, and the other is scalar, no?
No. I would.
P is several variables, so just ordinary derivative.
Also, yeah, here is not such. Sorry, I write. Usually, this equation is energy conserved. Which energy? They conserved such energies. Q, nabla, U, Q. This is the energy equation. And the Q can be vector valued operator. Q can be vector valued operator even. And then here the relation is that P.
Not just this. Time derivative of U also in the energy. It's not this energy.
Oh, sorry. It's plus something. I forgot. Yeah, perhaps. Yeah. Sorry. Yeah, perhaps this one. And the way we treat such generalized Hamiltonian system. And then we know this system, the solution of this system, we write it in a abstract space, and the solution should be, this is solution. And this is energy manifold. This energy manifold. The solution will go with the T and should keep keep on the energy manifold. It's a short system. And the question comes back, our applied mathematics. We don't know the energy. We have only finite state. We have only finite states. Then the simplex method thinks so. We cannot keep the solution on a manifold, and we hope the solution keep in a share of the manifold. We take some epsilon and build a share of the energy, and we hope to give a solution and keep in this share. And this means if you go around the mountain and you want to keep the height, okay, you go on the tangent direction, okay, and you find that you are lower of your height, and then you should come back. And perhaps sometimes they're too high, and then you come back, and then to approximate the circumference. And this is typical, the classical symplectic algorithms. Or this is our algorithm. Okay. And we come the next. Yes, this is one. Usually to solve such problem, we take the function v. V is the derivative to u, and then we can write the utt to a system, to write a system. And then here is this. This is the energy set, and here the operator Q and P is related with these equations. And if you write in Fourier transform, you can write in this equation. Now, at first we should discrete the equation in space. This means you should take some x, discrete finite x scattered on the x space. And then you get so-called finite dimensional Hamiltonian system. You get some curve, you get some trajectory. Only the behaviors of the leaf. You cannot describe all the water, and you can describe the leaf, and you should describe every leaf how to move the leaf, and you should describe the equation at first in the x to want to describe the leaf. And then you take the photos, perhaps. No, not photos. You perhaps take the video. You take a video. What is the video? Video is the description of time. There are a lot of photos. The video, in fact, is a lot of photos. Every leaf is perhaps a pixel. Only some finite pixel and finite many photos, and then you can describe a video. Video is in this way. Okay. Then we get this is image. We get such partial differential equation system and the energy. And if you make the discretization of the space, then you get such finite dimensional Hamiltonian system. And then you get a finite dimensional energy. It's energy. It's only an approximation of the energy. It's only this manifold is in the shell. However, perhaps in this form, I don't know. It's near the energy manifold in the shell of near the energy manifold and perhaps in different form. We don't know. Then we describe the equation in time and hope our solution always in this new manifold. And then we can take some idea. I think we have not so many time, and we have two methods. One method is describe the equation to the energy. We describe the equation at first, and to find the discrete energy manifold, to find this new manifold. One is from the equation. We take the equation, it's very easy. Then we ask it if they can keep the energy, a discrete energy, invariant, always invariant. And this discrete energy is an approximation of the energy manifold. This is our idea. And about some calculation, we get the results. I think it's not very interesting. And another method is come back. We discrete the energy. Yes, this is energy. Another method, we discrete the energy manifold. We don't know the energy. However, the simple method, for example, we want if we have a loop and to take a wave, yeah, and then this solution is the length invariant. The loop length is always invariant. And if we use divider difference, they take the chord length to instead of arc length. And then their method is always keep the chord length, the summation of the chord length is invariant. It's this idea, it's a basic idea, very good idea. Now I think why you not take better approximations method to approximate the length. They take the chord length to instead of arc length. The order of approximation is not very good, and we take better approximation method, and then we can take better approximation. This means the thickness of shear is very thin. You can take the epsilon what you want. It's always small and small. And then we derived two algorithms. It's only calculation. We derived two algorithms. One is from equation to energy, and one is from energy to equation. And this pair, the equation and the energy, this pair is coupled with the original problem. And both are the approximation of the original problem. And then we estimate, we discuss in time, and to keep the conservation of the discrete energy and get some results. If you want, the paper is already accepted, will appear somewhere recently. And then we make the convergence analysis, and yeah, okay, blah blah blah. Here are some numerical examples. The first example is taking simply the wave equation, the wave equation with a simple initial condition and boundary condition. It is, I think, it's a periodic solution. the true solution, we get it already. And then we calculate the energy. And calculate the solution, and this is true solution, and this is our approximation. Use our method and get the LU, and verify that. Here is the posterior LU. As this means we use the computer to calculate the LU, and we refine the mesh and calculate the LU again and again, and we get the posterior LU. And it is verified our prior LU estimate in last section. And another things, the classical symplectic method get usually such results. Get such result. It means it is tau is the time step, and h is the space of the x, the density of the x, and such results. And we can realize that we can get better LU estimates. And here we can get here. Here is already 2, and we can get 4, more than 2. And the second result is almost the same, however, what we want to see. In the radial-based approximations, there are parameters. The parameter is called the C. And we can adjust the C to get fine results. However, the C is, how to get the C is somewhat some theory back out of the discussion. I will not extend here. And here is another remark. One of the example, we find that our algorithms is not energy conserved. Energy is always decreased in one of the example. And I think this example is this mistake is happening because we take a wrong example. We take not perhaps some energy will move out from the boundary, and then we get however almost is conserved, and far away there are some small wave, and we cannot find it. We cannot find it. Okay, I will start.
Okay.